two papers by him, which have been very influential from, I think, 1987, together with Svensson. So it's the Wang Svensson algorithm, which is very famous. So Professor Wang studied first, as far as I can see, physics in China, and then moved to the US, did there his master's degree, and then with, I think with Svensson, his PhD. And during his PhD, he just published these two influential papers. And he further then worked on different topics of statistical mechanics, also things related to more to material science. But in the last time, he has a little bit switched and has come to more non-equilibrium questions, green functions, thermal transport, Hall effects, and things like that. And he will give his talk today on quantum master equation approach to transport. Please, Jian-Sheng, may you start your talk.
Thanks, Professor Tokna. This is my homepage, and in fact, I have already posted my talk online. If you are interested, you can go over there. Okay, so I thank Georgia and the organization committee for inviting me for this special colloquium. So I guess I'm supposed to be a kind of a general talk, but I don't know, maybe my talk is a bit kind of specialized. Okay, my title is Quantum Master Equation Approach to Transport. I guess my term transport is a bit too general because transport can mean many things. So what I'm really mean by this transport is nanostructure. So I don't really look at these bulk transport, but nanostructures. Okay, I need to make a kind of a disclaimer. So quantum master equation, I'm not an expert on it, and I also don't do it full time. I'm a part-time quantum master equation researcher. Georgia is one of the one who actually get started on this topic. So I will mention a little bit on this when finally I make a acknowledgement about this. Okay, here's the outline. So since I'm not really kind of a traditional quantum master equation person, I would like to look at this problem from a non-equilibrium green function perspective. So we try to understand it and try to derive the equation. So we end up discover something. And so that something is that if you really try to look at this reduced density matrix, and if you try to expand them from a kind of adiabatic switch on of the interaction, and we found it's actually divergent. And the divergent is quite serious because it's not the sum that is divergent. It's actually each term is divergent. And only the first term is not divergent. That is usually the one people use. But all the higher order terms are actually divergent in the form of 1 over epsilon. So I will explain what is this epsilon here. So that's the first point. Maybe this point is well known, but I don't know. Maybe Georgia is more connected to the people who do math equation. This is well known or not well known. Of course, if we go back to the literature and look at how this math equation is derived, it's actually kind of you have kind of an eliminating process. So there is by doing this eliminating process, you actually remove the divergence. So in the end, the actual quantum math equation don't have this divergence. So that's one point that we learned. And the second part is that we can actually do some shortcut if we are interested in higher order contribution. And this shortcut, we call it analytic continuation, AC. So we have a certain situation that this works and it's good. Here, when I say works or good, I mean it works exactly. So it's exactly what we're supposed to be. And but there are one example at least, they doesn't work. There is kind of an error. So we are not really completely understood. And there is I would challenge some of the young people to try to give a precise criterion as exactly when it works and when it doesn't. It's kind of a tricky situation. Okay, so those are the kind of a theoretical side. Then after that, I will try to give you 3 applications on the use of this quantum matrix equation to do with the phonons and also the thermoelectric effect and the interface problems. Okay, that's all my outline. This is a picture that everybody know when they study quantum mass equation or open quantum system. So the general framework is that we are interested in a small system, a finite system, so we call it system. This system is connected to a bus. The bus is supposed to be infinite in extent, so very large. So usually we will not really terribly interested in the one bus situation because the one bus would just give you kind of an equilibrium. In the most general situation, at least we should have 2 bus. So we have a left bus, right bus. So in that case, we establish non-equilibrium situation. So that is more interesting. Usually, we will have a small parameter to begin with so that we can make an expansion. So in this framework of an open quantum system, usually we take this coupling as the expansion parameter when we try to do perturbation theory. So that's the point of view that we try to take. So we try to develop a perturbation theory in this coupling. This is in contrast with the non-equilibrium Green function, we call it NEGF. So in NEGF, this coupling, if the coupling is linear, we can treat them exactly. So there's actually a kind of a comparison that we can make. So we can see if this expansion and compared to a theory that is do not require this to be small, how does this to compare? So in general, you describe the system by kind of a density matrix, which take the geometric form of this following form with this weight to be positive definite. And so this is the density matrix of the whole system, but because the bus is typically kind of boring, and we make a certain assumption about the bus, so we are not really interested in the bus. So we will actually trace them. We trace out the bus. Maybe I should put a B here to mean that I trace out the bus. And then we try to see what is the equation that the density matrix have, or in other words, we can we predict what is this rho? As you will see that when we study transport, it turned out that the rho itself is not enough because we should simultaneously also look at what is the current. But usually this current is actually an operator that involves the bus itself as well as the system. So, so that is kind of a feature that focusing on the rho is not enough. We actually have to have both rho and I. Okay, so let's try to do something that is quite usual in perturbation theory that is called adiabatic switch-on. So in other words, we are going to say that at the t equal to minus infinity, we have a decoupled system, we have a bus, we have a system which are not coupled, and we turn on this coupling slowly. And at time t equals 0, we have the full coupling. So that is the perturbation that we want to do. So in order to do this perturbation, we take these 3 pictures. People study quantum mechanics or many body theory must know this. So we have the Schrödinger picture. So in Schrödinger picture, you focus on the wave function. So the operator itself will be not dependent on time unless you have an explicit time dependence like the one that we have over here. That means this time dependence is not evolution, but explicit time dependence. And so we need to solve the Schrodinger equation for the wave function. But in the Heisenberg, this is kind of equivalent. So basically, you transform the time into the operator. So now the operator depending on time, but the wave function should not dependent on time. And usually we have a so-called synchronization time. We say that at t equal to 0, the wave function is the same as the Schrodinger wave function. But both of them has certain advantage, but for practical calculation, it turned out that this interaction picture is the most appropriate for real calculation. So in this picture, we have a kind of a mixed representation. We say that this operator follow this non-interacting Hamiltonian H0, and the interaction still have a Schrodinger equation, and that Schrodinger equation controls this evolution of the wave function. So in the next slides, I will.
Sorry, Prof. Wang.
Yeah.
We have a question from one of the participants. Shankar, please, could you ask the question?
Okay, you speak, or you have some message?
No, Shankar, please, can you unmute yourself and ask the question? Okay, it seems that the hand is raised, but there is no question.
Hand sorry,
is raised,
I
am sorry to interrupt your talk. Yeah.
Okay, you just speak because I couldn't see the hand.
Yes, no worries. Please, we carry on. Thank you.
Okay. So the idea is that we are going to evolve. So because what we are really interested in is density matrix at a later time, t equals 0. So we are going to evolve from a product state, which is completely decoupled. And the important point is that the bus itself will be thermal. We have a thermal bus state, and we have an arbitrary system, and it's a cross product. It's a Cartesian product of these two. And that state we're going to evolve adiabatically, and at time t equals 0, it will be the density matrix of the interest. So the question is that can we actually do this? So I'm putting a question mark. So that will be the next page that I'm going to look at. So what will be my time? So I'm supposed to stop at for your time.
Yeah, you have a good 30 minutes.
30 minutes.
35
Still 30 minutes.
Roughly.
Okay.
Yeah.
Okay, something like 20 past hour. Okay, so this is what you have at infinity, and then you evolve. And you evolve according to, as the previous picture implies. So you evolve according to this, and you put the time dependence into the V, and that is the kind of evolution. So here, this evolution is, I have this contour time. The reason is that this evolve, you see that on one side is going from 0 to minus infinity. On the other side is from minus infinity to 0. So you can think of this as evolving, going backwards, and you going forwards. And so in general, I could introduce a tau, and this tau is a so-called Keldysh contour. It's actually going from minus infinity to plus infinity going back, but you can actually cut them off because this part gets canceled. So that is sort of a kind of a notation that I'm going to use. So I have this contour order operator, which means that this operator has to be ordered according to this contour here that I have drawn here. Okay, this can be done. So this is quite standard. Now, this slide gets very messy. It's a bit kind of complicated. Basically, I'm going to look at kind of a Dyson expansion according to this evolution. So I focus on a particular operator, let's call it O. So it turned out that this density matrix itself can also be expressed as kind of an expecting value of some operator. And it turned out that that operator is a so-called Hubbard operator. So this is known in people study quantum mass equation. It turned out that, okay, if I look at the Mn, entries of this matrix, I need to transpose it. So, so in this formula, rho itself is not a abstract quantity, but actually is a matrix. So, so because X is a matrix, here you transpose it, so the result is matrix. Okay, so this evolution has two pieces. So the way to look at these two pieces is you combine them. If you combine them, it becomes one single piece. And so this one single piece can be expressed by this contour ordered operator. So, so this has certain advantage in notations, but it's don't really have kind of a deeper physics. So basically, either you you use the commutator, or you use this contour, which is sort of equivalent. So here I don't have a commutator because I'm putting these two kind of together, put it on the contour. So here in this integral, so that means that my tau is actually something like this. So I write from minus infinity, going start from here, and then go to the time t, then coming back. Okay, so this is a kind of an exponential. You can expand them, Taylor expand this exponential, and you get various terms. Here, I'm going to use the fact that my coupling V is linear in the Basque variable. And so if I take an expansion value, I assume the odd power will be 0. And so I only need to take the even power. And that's why I only have either first zeroth power or second power of power. So in other words, the result will be only, so this is essentially the same as rho 0. The correction is actually second order in coupling. So I will not try to introduce actual notation for the coupling. It turned out that this coupling will be exactly this particular combination, minus IH bar. So formally, I take this as my coupling parameters. Because we are studying kind of a transport, and we also want to derive equation, it turned out that I also need to take the derivative if I try to get the equation for something. So taking the derivative, you actually have three pieces, because one is in the operator itself. That is a Heisenberg operator or interaction picture operator. Then I also have one from here and one from here, and that combination can be written as a commutator. So as a result, if I take the derivative, I got these two, basically three terms, the explicit term and two of these commutators, and that has to be multiplied by this factor here. Let's see, maybe I made some error. I guess this, I need to move this bracket over here. Yeah, that was the error. So, so I'm talking about the divergence. It turned out that these terms are divergent. So it's not too difficult to work out some of the concrete terms. So in general, we have to compute something like x to the t, which is the Hubble operator, and the v to the n. So here n has to be equal 2 or 4 or 6. And this term can be regrouped. And if you take a certain eigenstate representation of the Hamiltonian of the system, so in other words, we're going to take the eigenstate of the system with the eigenvalue of the system. And if you try to make an expansion and do the calculation, actually the calculation involves an integral here. So the number of integral here, it's a proportion to the power. So if you have a v to the 2, you have to integrate twice. If it's a 4, you have to integrate 4 times. And it turned out that if you do this integration, because you have to integrate from 0 to infinity, and that produce kind of a divergence. And this divergence is given by this one. So actually, it's not always divergent. It's only divergent on the diagonal. Because on the diagonal, there is this delta, and this delta is 0, because this is the hopping energy of two levels. So, so on the diagonal, this is a 0, and you actually have a divergence, which is this epsilon. So remember that this epsilon is my adiabatic switch on epsilon. So in other words, I have to turn on this interaction, but if I try to gradually switch it off,
Hi, Professor.
it's actually divergent.
I want to interrupt you. Jungyun Han has a question. So Jungyun, unmute yourself and ask.
Yeah. If you have question, you just speak.
Yeah, hi, Profan.
Yeah.
I have a question. Did you consider any, just because you mentioned that any expectation value of the old power of V would be 0? Is it,
That is
is
my
it because
assumption.
of the, you consider some quadratic or even power Hamiltonian?
That is my assumption of my model. Let's see. Okay. So basically, I say that my coupling is a system cross bus, and so will be the Hamiltonian of the bus has to be quadratic in B. So this is the Euro assumption. So that is usually applied, but I don't think this will be very critical, because if it is not 0, you can redefine it. You can still remove the R term.
Yeah, thank you.
I think that point would not invalidate this divergence. Okay, so that means that if I try to use this kind of expansion, it will actually don't work. So what's the problem? The problem is that when I can choose my initial state in such a way that I can cancel this divergence. So maybe I show you the next slide. I have this series here. If you go back to this one. So if you look at this equation, so this equation is actually a mapping that maps your initial state to a final state. So this is your t equal minus infinity state, and this is the t equal 0 state. And this mapping is actually a linear, because if you take a combination, it will be, if you take lambda, it will be lambda of that. So it's a linear mapping, and this mapping imply that this mapping are not well defined, because they are each one of the coefficient is divergent. However, you can still formally invert them. So I'm going to revert this so that it becomes a mapping from row to row 0. So that can be done. So this when you do this, you can formally rewrite your mapping as I'm mapping the row back to row 0. And remember that there are still divergences over here. So, however, if you plug this back into the first equation, the equation about the derivative, that is, I didn't write it more explicitly. That is this equation that you can do a kind of a similar transform expansion. So if you substitute that back into here, what you get is the standard mass equation. So this is actually the this is the standard mass equation to expansion to all orders if you continue expanding them. And it turned out that this particular expansion do not have that problem. So so this is so this become an equation. So so this equation is the Euro one. So so what is the lesson learned here? So I'm still kind of don't know what's the real implication of this. So what does this say is that you cannot choose arbitrarily your initial state. You have to choose a very special one, and that special one corresponding to this inverse map. Basically, so this rule has to be solved. If you look at the steady state, you basically solve that equation. When you solve that equation, then this rule 0 in some sense is fixed. So this looks like a bit strange, because we are supposed to forget the initial condition. So we are supposed to not remember what our starting point is. But clearly this map seems to indicate that it does remember. And as long as when this epsilon is not, when this epsilon is exactly 0. So I guess it has something to do with the limit that of this adiabatic space on limit this epsilon. Okay, so how do we solve this equation? So this is quite standard. So when we try to solve this equation, we try to solve it order by order. So we have this small parameter lambda, although it's formally. So usually we will truncate all of them. and we just keep this lambda square. So if you do that, what happens is that it will be only correct to the 0th order of row. It will be not correct to the linear order of row, because the linear order of row, it turned out to be determined by a 4th order of row. So there is kind of a general statement on that. And so if we do that, we can get a series of set of equations. Here is what I write the first two equations. So basically, we expand the 0th order and the first order, and it's better to separate the diagonal and with the off diagonal. So here we have this Hubbard operator. So this one is the purely diagonal one, and this F is the purely off diagonal one. And so you can write it as sum of those two. And so when you separate it out, you will get a series of equations. So to 0th order, the off diagonal is 0 exactly. The first order, the 0th order row is determined by this equation. So it's like a kind of a detailed balance equation. So so if you are interested in the 0th order, and that's one that is only one that you need to solve. However, if you want to solve the 2nd order, then you have to go on to the 4th order. And so basically the 4th order has an equation for the off diagonal, but the off diagonal is easy because the off diagonal just need to know what is the diagonal, and that's it. So this is actually very easy to compute. But the diagonal is very complicated because the diagonal couples to the higher order, and you have to work to the 4th order in order for the diagonal to be correct. And so we are not happy to try to solve this. And Jose and I discussed how do we solve such a thing. And we decide, let me skip this, that we should actually do something clever. Maybe I will come back to this and talk about this 2nd order, because this is one of the points that we want to discuss. So it turned out that we can do some shortcut. This shortcut, this is the same equation as before. So of course, we focus on this equation, which we can solve. So when we solve this, we get the diagonal one to 0th order, but we also need off diagonal one. The off diagonal one is given by this. And what about the diagonal one? The diagonal one, we are not going to solve this equation because it's too complicated. So what we did was that, so this equation, you should think of that, this is actually kind of a matrix. So you have the indices m and n. So this m and n are integers. So they take, say, 1, 2, 3, if it's a boson, or 0, 1, 2, 3. But even if the electron is occupied, not occupied, it's also integers. So, the question is, can we actually use this formula itself and try to get some information about this diagonal, starting from the off diagonal? So in other words, I know my matrix, which is known exactly on the off diagonal, and can I take kind of a sort of a limit so that I get the diagonal? So if you look at this formula very carefully, it's actually this delta is actually E of n minus E of m. So actually, according to our definition, we divide by h bar. So if the diagonal is approached, this actually the denominator is 0, but the numerator is also 0 because that is precisely sort of this equation. It's actually a 0 by 0 kind of form. So the question is, can we actually do this limit? So the answer turned out to be yes, we can take this limit. So here is a more concrete formula for that kind of somewhat more abstract formula. So we can write this in terms of the actual density matrix of the diagonal one, which is the solution of that kind of a mass equation, the Euro mass equation. And so we are going to take this equation and try to take the limit n goes to m. So what we do is, okay, we do this in NH because it's controlled by NH, and NH goes into the denominator and also goes into the numerator, and actually goes inside this W, which is the bus correlator. And so I will skip the detail because it's a little messy. So if you do this and you try to say, okay, let's take a complex number, and we found that the limit does have a kind of a unique answer to it. So we have a prediction. We have a kind of a formula to get the result. And so obviously this is kind of a not too rigorous kind of argument from a mathematical point of view, but let's try to check whether this works or not. So here I have a kind of a slides to summarize whether it works or not works. So so does AC, so analytic continuation works or not? Let's look at several situations. So in one situation is that let's have only one bus. So if you have one bus, the system actually is equilibrium, because particularly in the weak coupling is the equilibrium. So Jota has made a proof that this really works, because in this case, you can compare with something called the canonical perturbation theory. So if you do the canonical perturbation theory, you found that that's exactly what you get. So the analytic continuation formula and the canonical perturbation theory match exactly. So in fact, for one bus, any system, it works. So what about two bus? Two bus, we can also compare, because two bus, we have this NEGF result. We know exactly what they are. However, the formula is a bit messy. So Jota made analytic, numerical check. So numerical check shows that yes, even for two bus, if you put harmonic oscillator there, it also works. So this works. So later on, we also did a two bus spin-Boston model. This is also calculated by Jota, and the spin-Boston model also works. And what about the quantum dot? So quantum dot, one single dot, meaning that my Hamiltonian is actually very trivial. It's epsilon c dagger c. So with one energy level occupied or not occupied. So in this two bus single quantum dot, and Dr. Xu also did a numerical test. I think, did we did analytic or numerical? I think maybe semi-analytic. So this also checked. We decide to do something fancy. Let's look at two quantum dot, but it turned out that this don't work. But don't work seems kind of a disadvantage. It's kind of a disappointing to us that we found the example that it didn't work. But maybe that is kind of expected, because the theory is sort of kind of not so rigorous. So I would be not too surprised that we found a situation that it didn't work. However, I would agree with Jota that even though this didn't work exactly, so it didn't work exactly, but actually, if it's close to equilibrium, meaning that it's these drives are not too far from equilibrium. In other words, in the linear response regime, this is actually quite good. So it's better than Limbrad so we have a kind of a numerical test on that, and people, you can read that paper to see the kind of the situation on that. Okay, so I'm more or less finished my kind of a theoretical aspect of this. Anybody has any questions? If not, I will go back to my omitted slides. So we are not particularly satisfied with just working on the second order by this analytic continuation. So we decided we really try to solve this equation. So the rest of the several slides is about solving this equation. So solve it. So solve this equation means that we have to compute this v to the fourth terms. So this involves 4 of those. Basically, you have to have a b 4 times in various combinations. So it's actually rather kind of a messy calculation, but it can be done. So if we do this calculation, we can actually get the second order term. So why we want to do this second order term, I need to go back to one of my earlier slides. That is the current. So if you look at the current, you can write it in this form. It involves this. So here I'm taking the phononic system as example, not the bosonic one. The bosonic one, phononic one. So so if you take the current, it involves this coupling. This coupling is it involves the bus P, bus momentum, and these system variable. So because of this, if you just have the Dyson equation solution, you can still cannot predict the current unless you are just happy with the lowest order. So if you are interested in the higher order, you have to actually work out a specific equation for itself, very much like the Dyson, very much like this Dyson, very much like the mass equation itself. So that gives you the following formula. And so this is the Euro one, but you have this fourth order one. So if you want to work out the result to fourth order, because the lowest order is actually already second order. So you want to go to one order higher, you have to actually not only know what is this rho, but also you have to work out this fourth, you have to work out something like V. And so that sort of a correlation. We can do this calculation. We can actually make some diagrammatic kind of expansion, diagrammatic representation of that. So, so this diagram actually means this wiggly line is the bus correlation, and this square is actually your rho. Then you have this arrow, and that arrow, depending on the direction, is either time ordered or anti-time ordered. That's because when you try to do this expansion, you have those sense. Okay, so with that, you can actually do a calculation. So here, basically, we are benchmark our calculation. And so we can actually do this single quantum dot result. And this result, NEGF or non-equilibrium function can solve it exactly. So basically, we are comparing that. So comparing NEGF with the mass equation result, and they match exactly, and that is basically says our code is correct. So that's not terribly interesting, except to demonstrate that our code is correct. But here is something more interesting. So here is a spin Boston model, and this model, spin Boston model, cannot be solved exactly. And so, so in some sense, this is a kind of a new result. So what we are plotting here is A2 and A4. So A2, A4 is the expansion in terms of this coupling, and 8 is the coupling. So here we see some kind of a interesting result. So if you look at this high order process, this kind of a oscillatory process. So I think we try to interpret them as co-tunneling. In fact, this is a purely numerical result. Actually, I don't have a nice physical picture why they are doing this. So anyway, so it's possible to go to higher order. Let me switch topics. Now, briefly discuss this kind of a phonon transport. So in phonon transport, I have mentioned this NEGF method several times, but let me show the formula here. So this NEGF formula, known as Landau-Karoli formula. So this is kind of a formula that can predict what will be the current if you have a situation that look like this. And you have a kind of a center, you have a left lead, right lead. But the restriction that you have is the Hamiltonian has to be quadratic form. So if the Hamiltonian is quadratic form, then this is the exact one. But if you have a nonlinear one, of course, you will have a little trouble. So, so here I'm trying to look at a Hamiltonian that is kind of a oscillator in the center. So this is the oscillator in the center. You can have a 0-degree freedom. Then let's put a nonlinear interaction. So this nonlinear interaction is the fourth order one. So U to the fourth, and then plus the Euro bus, and the coupling to the bus. The coupling to the bus will be also quadratic. So you have this degree on the left, a degree on the center, which is those variables. So under such a situation, we have to modify this so that we have this coupling to the lead, which will given by the self-energy, and then we have the extra term. So this extra term is this mean field approximation. It's actually quite kind of surprising that this mean field approximation actually works very well. So what you do is that whenever you have this 4, you can decouple them into 2 and 2. So you get 3 terms. So roughly speaking, you have 3 of those. And with those, diagrammatically, you can think of the kind of okay, this bubble diagram that is stick there, and this 3 is the combinatorial factor. And so here is the result. So the result is that if you do this self-consistent phonon, which means that you get this green function G less, and this has to be determined self-consistent, which means that you have to solve this, and you get a green function, and you have to plug in using this relation between G less and GR, and you have to redo it until it converge. And however, mass equation can do it exactly, but the catch is that in the mass equation, the coupling has to be weak. The coupling, I think, coupling is different sample. I think this this corresponding to weak coupling, this corresponding to strong coupling. So curiously, they actually match very well, almost exactly. And there is another plot that that is more recent. So so this is a kind of a oscillator problem. So you have kind of a left lead, which is a certain bus. I think we are not using Rubin bus. We use some Lorenz-Zut bus. So you have a bus here, you have another bus, and then you have either 1 or 2 oscillator. I think for this particular plot, I'm using one of these oscillators. So this oscillator has a nonlinear interaction of a cubic form, and here this lambda is the coupling. So you see that when the lambda increased by a factor of 10, this agreement is still as good. So they are almost perfect. So the NEGF and the mass equation is perfectly matched. Let's see, the coupling in this particular case, I think it's, it's a lambda. Lambda is the coupling, gamma is the bus parameters. So that is a bit surprising because, in fact, we do this mean field. We don't really know how good they are, but now we have kind of a understanding that this is actually very good. But the trouble is that we cannot scale this very large. So that's always the case. The quantum mass cannot really scale up to very large systems. So when they scale very large, you have a kind of a mean free path. Maybe at that point, there's something will break down. But anyway, that is sort of a thing that we have. Okay, another topic that, let's see, what I have is this time-dependent drive. So this is, you drive the system with the time dependence, and you look for the transport of this, both the electrons and the energy. So the center here is either you put it a quantum dot, actually just like this, and your drive is this on-site potential. We may or may not put this electron phonon interaction. You know, we put a phonon here, but for simplicity, let's ignore this. And this is quite standard. You have the bus, left bus, right bus, and the coupling. So that is the problem. So so why this is interesting? So the interesting that is that if we drive them, we can go far from thermal equilibrium. And if it's far from thermal equilibrium, it turns out to break the orthogonal relation. So the orthogonal relation actually a breakdown of orthogonal relation actually can give you kind of a higher efficiency. But how do we determine this orthogonal coefficient? So I will write down in this column vectors here. You have a chemical potential bias, you have a temperature bias, then you have this drive. So this drive is actually a functional because this drive is goes into here. So it's not a one single number, but it's kind of a function because we can choose it to be in certain form. So in order to actually consider this so-called the linear response, we actually try to look at the current which has two types of current. We have the electric current and the heat current. And so we look at this current and we try to extrapolate when this delta T and delta nu is equal to 0. And so this will be the kind of a sort of a fit to this one. And so basically this gives you kind of a slope that is this L. But you also have an interception. So even if you put this exactly 0, you still have a current. That's because you actually drive them. So that will be the last term. So so here I use this notation. That means it depending on this in the functional form and not really kind of a number multiplying it. Okay, with that definition, we can define a kind of efficiency. So basically, this efficiency is how much work we are doing. Actually, we kind of we need to put a circuit here. So here is our resistor, and when this produces a current, it actually make work to the resistor. Then the denominator has three terms, which is the heat put into it, entropy flow, Peltier heat, and geoheating flowing back. Actually, I get lost. So my student did this. I'm not quite understood his formula, but it's supposed to be coming from this book. And so this is a sort of efficiency, and this efficiency eta actually goes into this this factor, of course, is the Carnot efficiency, and this is the actual term that goes into it. Okay, so we basically look at this efficiency as one of the parameters. So basically, I show you the result. So if you have, if you try to put a kind of a step, so this drive is you have no drive, then suddenly you make a change of your on-site potential. So when you make a step, you found that initially it's sort of in steady state, and later on it's in another steady state. But when you drive them, its efficiency actually increase, but also go to negative according to our definition of efficiency. So this quantity is the breakdown of the Onsager relation, because the Onsager relation implies that the 1, 2 is equal to 2, 1, but indeed it breaks down. So initially its Onsager relation is fulfilled, but at the long time it's fulfilled. But while you are driving them, when the current is kind of making change, it breaks down. So let's look at the another slide. So this one is you have a certain waveform. So here I have a kind of a delta peak. Here I have a kind of a box here. Here I have a sine wave. So when you drive them, you will find that the Onsager relation continues to restore to 1 or break down depending on the time. And this efficiency indeed is bigger when you drive them. So this is one of the points that we show that indeed, if you drive them, you actually have kind of efficiency, and hopefully this makes sense. Okay, I don't have much time anymore, right? How much more time I still have?
About 5 minutes.
About 5 minutes. Maybe I can still say something about in 5 minutes. Okay, let's see. Okay, I need to do something. This kind of funny. Okay, so in the 5 minutes time, I talk about another kind of a problem. So this problem actually, the spirit is very much like the mass equation, but actually, in this case, I'm thinking about or try to calculate something that is left lead, right lead, no bus. Sorry, left bus, right bus, no center, no center. So in other words, my Hamiltonian is purely just left, just right, and the coupling between them. So, so because of this, it doesn't seem to make any sense anymore to talk about the rho anymore, because there is no such thing. There's no degree freedom associated with it. So how do we do calculation like this? In fact, we can still do calculation. So the formal apparatus still works. We can still do the perturbation, but it turned out that it will be much more useful. We just focus on the lowest order for kind of a contribution. This is sort of like a linear response. So we are doing the linear response. We assume that these coupling are weak. So here in this particular calculation, I will show you the two type of calculation. So basically we say that I have a left lead, which are phonons. So here I have a phonon system. Then I have a right lead, which are electrons. So on one side is a complete insulator, no electrons. On the other side, it's a metal. So this is actually an insulator metal interface. So this is the Hamiltonian for the metal, and this is the Hamiltonian for the phonon. And there is this coupling. This coupling corresponding to the hopping. So when the electron hop, you will actually lose energy or gain energy, and that energy can be supplied by the phonon itself. So basically, we are looking at this electron phonon coupling interface. And it turned out that we could also have a situation that has 3 lead. So here I have a phononic system. Then I have an electron here, an electron there. And so this can be used as kind of a thermoelectric device, because if the electron hop from one lead to another lead, actually, I should take it back. The electron cannot really hop because I don't have a direct coupling for the R1 and R2. So what happened is that the electron can lose energy and pass it to the phonon, and the phonon gave it back to the other side. So so this energy transmission can be used to do some kind of thermoelectric device. Okay, so that is kind of a setup. Maybe I can skip some of those details. So here is sort of the formal Hamiltonian. So I have this coupling here. I have a left and I have a right. And so the coupling will be only depending on the bus degree of freedom. So B is something. So let's look at the particular X. So this X is commute with the bus because so I'm interested in something that is conserved. So so X can be either the particle number or the energy Hamiltonian itself. So with this, we can actually do the linear response using the same kind of expansion. So we are just keep it to the lowest order, and the lowest order means that it's V times V. So we ignore the high order. So this is in that sense is approximate. So you can actually rewrite this into kind of an integral, and this integral require you to evaluate 2 types of kind of correlations: the bus correlation for the right, and the bus correlation for the left. But for the left, you have to take this commutator because this corresponding to the rate. Okay, skip the details, and let's show you a kind of a plot. So here, what I'm plotting here is I'm actually taking a 3-terminal situation. So now I have a situation like this. So I call this left. I have right 1, right 2, and so what happened is that even if I have a same temperature, so T1 is equal to T2, so there's no temperature difference over here, but I do have a higher temperature over here. So this high temperature can actually pump in energy, and so that the electron, you can get a heat current that seems to be obvious, but curiously, you can also get an electric current. So in other words, this can generate the electric current. So there's a control parameter. This control parameter is on site. So basically, this one single quantum dot. Sorry, not one single quantum dot. It's actually a Rubin chair. for the photon, it's sort of a 1D chain for the electron. So the electron actually can basically, if your parameter is right, you can generate the current continuously. So here is kind of a plot as a function of the temperature. So that is kind of a thermoelectric one, but recently my earlier student, Zhou Huanbo, by the way, this is also calculation by Zhou Huanbo, yeah, my student, earlier student Zhou Huanbo. So in this situation, we are basically we are going to replace this the lead by a different one. So in this case, both of them are phonon, but we couple them in the cubic form. Actually, we couple them in a form that is, for example, left, right square. So we couple them in right form, in this form, and look at these conductance, which is how much NH per temperature bias. And so this conductance, so if you take these standard two phonon or quadratic coupling, you found that they saturate. So they saturate quite quickly. So they saturate for three different situations like graphene, and graphene at S1, S2. However, if you take this cubic interaction, it turned out that this cubic interaction give you kind of a linear dependence. And so it goes like T. That is sort of surprising. So, but we can actually interpret this also in the classical framework. So indeed, this linear dependence is due to this cubic coupling. I think I'm more or less done. So I would like to thank 3%, which is in this picture. Jose, he was my postdoc for 1 year. We don't know master equation at all. He gave a series of lectures on it, and that is the starting point for Jyoza to work on this topic. And so Jyoza became an expert in it. And so Jyoza continued working on that. And the follow-up work is by Hombo, and Hombo now is in the institute in Singapore, and he continued working a bit on this mass equation. As for myself, actually, I don't really work it. I just gave the talk that they did the work, and I'm trying to summarize what they have done. Okay, I'm ready to take questions.
Okay, thank you, Prof. Wang, for this really nice talk and this zoo of different transport setups. So we have a question in the audience from Tobias. Please go ahead, unmute yourself.
Yeah, thank you for this really nice talk. I would like to have a question to the first part of the talk, namely this perturbative expansion of the master equation.
Yeah.
And especially, so this first contribution that is of the order of lambda squared is the usual Redfield equation.
Yeah.
And now I wonder what this fourth order, what the form of this fourth order contribution is. And is there any hope that this cures this inconsistencies of the Redfield formalism? Is it then of Lindblad form, for example, or can you make any point about this?
Well, if you the Euro cutoff, if you do the Lindblad, you cut off at the second order.
Yeah.
You cut off at the second order, so you ignore this term. So so if you keep this, you can only get the zeroth order correctly, and you do not expect your second order is correct. So this is not correct, which is well known. Not correct in the sense of perturbation theory in this small parameter.
Yes.
So that may not be important because suppose you want to calculate the current, and if you are able to the lambda square contribution, that's good enough. So it will be, the error will be propagated only at this level. Is that really what you
Okay. And when you
that's what I can say. So
okay.
Yeah.
Probably together with this fourth order, it becomes consistent then on the second order.
Yeah.
Okay.
So it will be considered in second order, but not considered in fourth order, because if you want the fourth order, you have to go to the sixth order.
Yes. Okay. Thank you.
Yeah.
Okay, sorry, next in the line is Jungyun. Please unmute yourself and ask the question, please.
Thank you, Prof. Fang, for nice talk. Just my question is about the initial state we have to choose, because I mean, in NEGF formalism, we have to choose, let's say, product of thermal state as an initial state, right? Then, and also we have some ambiguity of the, let's say, system temperature parameter.
Usually in NEGF, it will not depending on rho zero, because in NEGF, if you say that you run long enough, it will actually forget about the initial state contribution. So it will be just determined by this bus, because you have this Keldysh equation. So the Keldysh equation has a term that is related to the initial state, but that term turned out to be zero. So if you do an NEGF, it doesn't have the same problem as what I had here on the mass equation. So I don't really understand the deep meaning of this, but you don't run into problem at all in NEGF. Because NEGF is working with the Green function. It don't really work with rho itself.
Yeah, but once you consider now some nonlinear interaction in the system, then you have to use Wick's theorem. Then to make a valid Wick's theorem for that, then you have to keep some, let's say, quadratic order of the, let's say, system Hamiltonian for that. Yeah, so the initial state wouldn't be arbitrary in that case.
Yeah. In that sense, it's not arbitrary. In the so in that sense, you still need certain property of this this initial state. So here in this expansion, initially I say, okay, let's the initial state really arbitrary, and in other words, not only the initial state is arbitrary, the Hamiltonian of the system is arbitrary. And so maybe that's the problem that runs into this problem.
Yeah, so I mean, just because we have a still degree of freedom to choose some temperature of the system. If we choose the given state,
it's supposed to be whatever temperature you choose is supposed to be not depending on it anymore.
Then can it be just arbitrary, like a zero temperature, or?
Are you talking about this mass equation expansion or this standard NEGF? If the standard NEGF, it does not depend on the temperature of the center at all. It will just consumed by the bus.
Okay. Yeah, I see. Yeah, thank you.
Okay.
Sorry, Andre has a question as well. Andre, please go ahead. Sorry.
Yes, hello.
Yeah.
Can you hear me?
Yes.
Okay, since this is colloquium, I guess this is appropriate place to address some fundamental questions. And I have a question or comment to your very first slide, I would say, very first, where you have the bus and system interacted to each other.
Yeah.
So in overwhelming majority of papers devoted to the bus system interactions, one considers the infinite set of linear oscillator as a model for the bus. But in many aspects, this model is pathological. In particular, it does not have the property of self-summarizations. And to have the property of the self-summarizations, the bus should satisfy the eigenstate summalization hypothesis, which we heard yesterday. Or in the other words, it should be chaotic in the sense of the quantum chaos. Then there is a theorem by the Michael Brehm, who is great expert in the diabatic theory, which says that there is no adiabatic regimes for the quantum Hautic system. In this sense, would it imply that any approach which based on the adiabatic switching of the interactions will fail?
Okay, that's good. So yeah, if we can, in that light, maybe this just show that what happened if we try to do this, to do the adiabatic switch on.
Yes, I guess one can mimic this system, for example, mimicking the bus by the set of the linear oscillator or by the interacting oscillator, which possess the property of self-normalizations. But I would say this is not the questions to your talk, it is just comment. Or I share with the audience the problems which make me feel uncomfortable with this approach of the adiabatic switching.
Yeah. So here we, if you try to think of from the quantum mass equation, the final equation point of view, the adiabatic switch is just an intermediate tool for us to get the equation. So we did this backward substitution to get to here.
Right, but you somehow assume that your initial states will adiabatically come to the, let's say, entangled states between the bus and the system.
Yeah. So we basically try to make such assumption that, so maybe this assumption really has.
I'm pretty sure that this is not always the case.
Okay.
Okay, thank you. Just comment.
Okay. So here,
in general,
we whether the system can be thermalized or not, we don't really care. We put it into the thermal state to begin with. So that is, that is the point of view that we take.
True.
Yeah.
Okay.
Thank you.
However, on the other hand, I don't really need to, maybe I did. Yeah, okay. I need to know that this coupling is sort of, coupling is linear in the bus. Do I really need to know that it's a quadratic? Maybe, yes, I need that because when I do this expansion, I assume Wick theorem, which in some sense, yes, it has to be a quadratic. Maybe if I take a more complicated Hamiltonian and then my expansion don't really work anymore. Because, so this expansion rely on the fact that, okay, formally this is still correct, but by the time you try to replace this V by the bus correlator, so at that point, I assume that the Wick theorem is valid. It could have happened that for some more complicated system, yes, you cannot do that anymore.
Okay, thanks. I just share my problems.
Okay, okay. I'll take a look at that.
Thank you. The one last question from Bijay. Sorry, please go ahead, Bijay. Unmute yourself, please.
Yeah, hello, Professor Wang.
Yeah, Bijay.
Yeah, so maybe a silly question. So this is about the last part where you talked about this three terminal. I'm still thinking about the mechanism of how you get electrical current in this case, because the electrons can't hop between the two leads, right?
The electron can't hop in the two leads.
So how current here?
Let's see. That's a good question. Electron can't hop between the two leads because there's no coupling. Sorry. That is of course nonsense. Electron can hop to the between the two leads, so that's why you get a current. So this Hamiltonian has CL, CR, CR1, CR2, I made the wrong statement. The electron cannot hop. Electron
No,
can hop through the interaction. Electron cannot hop directly.
Sure.
So there is no such a term, but there is such this kind of term.
Okay.
So otherwise, if you will just violate charge conservation.
Right. Okay. All right. Thank you, Prof.
Yeah.
Okay. Seems like that was the last question. No raised hands from the audience. So let us thank Prof. Wang for his colloquium talk and all the other speakers as well for the talk today.
Okay, so thank you very much, Joseph.
I officially end day 3 of our workshop, and I will keep this channel open just in case if people want to discuss for probably the next half an hour. If there are no discussions, then we can just carry on. I'll close the channel. So thank you all for joining in, but this marks the end of day 3. Thank you all.